So we're going to take one more day here with exponential functions, look at some application problems, and hopefully you'll be comfortable with this. I just remembered I wanted something else. All right. So in order to solve these exponential application problems, it's helpful to know how to write the function first. So let's start with that. And we'll talk about two different types of exponential functions. Exponential growth, so things are getting larger and larger, and exponential decay, things that get smaller and smaller. For each type of exponential function, we'll have that function as some y sub 0 times g to the power of x divided by t, where y sub 0 is the amount we start with, whether it's a savings account or a population or a radioactive element, whatever. That y sub 0 is our initial amount. For exponential growth, that g is then the growth rate. If it doubles or triples or quadruples or however it grows, that's going to be our g. And the x is just the amount of time, but t is the length of time for the growth rate. So if your money doubles every 6 years, t would be 6. And g would be 2, because that would be the growth rate. The exponential decay is exactly the same. The only difference is instead of a growth rate, we have a decay rate. And one thing I want to talk about with the decay rate is this is the amount remaining. So for instance, now a half-life, it's pretty easy because if half of it is gone, half of it still remains. But if we said like for some medications, after an hour, 25% of the medication has worn off. Our decay rate would be 0.75 because that's the amount that we have left. So it's always the amount we have left or the fraction that we have left for our decay rate. It's an important distinction. Excuse me. So examples. A certain population starts with 50 members, and it is expected to double every 8 years. What will the population be in 16 years, and what will the population be in 20 years? So to start with, we have a starting population of 50. It doubles, so we're going to have 2. X divided by the time it takes to double is 8 years. So one thing you'll want to be sure to check, and I don't think there are any problems in your homework where they talk about years and then give you time measured in months or anything. I don't think you'll have to worry, but you should always check that the measurements are the same. Years and years, months and months, days and days, hours and hours, whatever they are. So to find the population in 16 years, we would go 50 times 2 to the power of 16 divided by 8. And I did this on purpose. So we would have 200 members in our population. Again, we're assuming that that this growth rate takes into account any organisms in that population that don't make it. But I wanted one that came out as a very easy integer power, but they won't all be like that. So that's why the second one, we do f of 20, 50 times 2 to the 20 divided by 8. And that would be 2.5. So for this one, we would need a calculator, unless you know what 2 to the power of 2.5 is, which I don't expect you to know. I don't think anyone would expect you to know. But if we go to our calculator, 50 times 2 to the power of 2.5. And you could do it this way. You could do it 20 divided by 8, whichever, there's several ways you can enter it. And here we have an issue because we're talking a population. So I don't think there are 0.8 of these critters running around. So I would say round to the nearest whole number in this case. So about 283 would be a good approximation. And it is going to be an approximation. We should feel pretty confident in that because it's more than there were at 16 years, right? The population's a little bit larger. So we should feel pretty good about that. So that's an exponential growth example. We could also have exponential decay. So a certain radioactive element has a half-life of 30 years. If you start with 75 milligrams of a substance, how much is left after 60 years and after 80 years? So our initial value, 75 years, or 75 milligrams. It is a half-life. So we have half remaining every 30 years. So here we're talking about milligrams of a substance. So decimal answers are okay if we get them. finding that function value when x is 60. And again, we could just plug that right into our calculator. Although it is possible to calculate it without. 75 times 1/2 here. I'm going to use the parentheses to the power of 60 divided by 30. 18.75 milligrams. And then for 80 years, now here, the calculator again is going to be almost necessary. Because I would not expect you to be able to calculate 1/2 to the power of 80 divided by 30. All right, so let's take a look at that one. And again, I like the calculator because I can just go second enter and it brings back that last thing that I did. And plug 80 in there. And so it's a longer period. We should have less substance after the 80 years. And in this case, we see it is less. Let's go 2 decimal places. 11.81 would be a great rounded answer. And again, you know, that 80 years, that's almost another half-life. So we should be a little bit more than half of our previous answer. So just in general, that answer seems pretty accurate. All right, now for your favorite part of the day, your homework assignment. I will say number 8, there's kind of a, it says, what is the maximum population the world can sustain? And don't worry about that. That's not a necessary question to answer. So those 8 questions, if you have questions, feel free to contact me and I will feel free to answer your question. So we have this week and next week, there will be office hours both weeks on Wednesday. That following week, I think it's the 10th of March, there are no office hours. That's the last week of the trimester. And so that Wednesday is a day off for students. So, you know, enjoy that day off. It's not a day off for teachers, so well, I'll probably still enjoy it, but anyway.